Okay, is everyone able to see the screen?
Yes, maybe all the microphones are turned into mute now. So you can continue.
Yes, we can see.
Yes.
Okay,
Yes, we have your screen.
great. Okay, what I'm going to talk about today is basically at the heart of our energy problem, because all the energy that the sun is sending to our planet comes biomass, one way or the other. And what we have been taking out so far, the fossil fuel, is nothing else than old biomass. Now, some of that biomass, that fossil biomass, we are making into plastic. And at the end of it, everything that we have been using is becoming waste. Now, a large percentage of unused energy resources is available in landfills in the form of plastic and other biomass that is basically left there to degrade and make not CO2, but methane, which is way more dangerous for our climate than CO2 itself. Now, because of this, we are promoting a trifold catalytic biomass approach to make that waste into oil and energy. So our municipal waste is basically plastic and biomass with some metals and some other materials. They need to be shredded and separated. Then the biomass, via a wet process in an anaerobic digester, can become biogas. Now the plastic is separated in that wet stage and via catalytic conversion can become oil. That process has been mentioned by Mr. and today previously. We are using a different catalyst and we are using a different equipment, but the basic process is the same. We are taking that plastic and making it into small units, which is oil. Now, when we have biogas and we have the oil, then we have two products that can be sold. But the final reason why we can sell these products is because we want to create energy from there that we harvest. And this is the last part of my presentation. Current engines that use an internal combustion process to convert the energy in biogas and oil to energy, they are inefficient, very much so. Now, first part, I would like to show you our 3D plug flow anaerobic digester. As you can see from the pictures, this is not your normal anaerobic digester, because when you mix everything in a big tank and you have different bacteria converting different parts of the materials, you have a competition there which slows down the process. Because of this, we have designed a 3D plug flow, meaning we can locate different types of bacteria in different parts of this reactor and therefore increase conversion. At the same time, we can take the gas from one part of the reactor and bubble it into another part in order to create a higher level of methanogenesis, which means our yield for the biogas process is higher and the speed or the output per volume of bioreactor is higher. So this is one part that makes the process interesting, because we can reduce the volume of these reactors in such a way that we can think later of putting a reactor into any mall and have the waste being treated there rather than transported miles away to a landfill. In order to do the processing of the waste, we have to have it shredded. What you see here beside the anaerobic digester is a small shredder that is combined with a screw to transport the material into the pre-stage. And in order to avoid the typical processes, the process problems that come with this step, we have designed a new type of blades for our shredder, which take care of plastic enveloping the shafts and making the machine stop or grind to a halt, because they cannot take the torque that is required to shred this plastic. So these blades do the cutting while the feeding is happening. That way, we don't have to stop the shredding process often, and we are also able to take these blades out while the shafts remain in place, which means servicing also is much easier. So that way, we can shred biomass and plastic together and then separate the plastic by letting it float in the pre-stage of the digester. The remaining material then undergoes the plug flow process and creates the biogas that can be fed to the engine. Now, for the plastic, we have a process whereby we take care of the volume. As you may guess, the plastic is still wet when we take it from the anaerobic digester. Now, for the processing of the plastic, that is no good. As Hans-Henning Dudek already mentioned, he has to dry his biomass in order to create a feasible process together with the zeolite. And as I said, we are using a similar process with a different zeolite. And our first step is we are using a specific screw press to take in the plastic base, and then first we compress it, which means we are removing the water not by heating, which costs a lot of energy, but simply by mechanical pressing. Secondly, that pressing is creating a high intensity mixture inside the extruder, which preheats the material. However, it only preheats the plastic. There is no water there to preheat, which means that energy is saved. And then, similar to Mr. Dudek's approach, we have a reactor which recycles the material in order to make the plastic into oil, which then is collected in a separate tank. This work is done together with the UTM in Malaysia. This is the university team. And well, I'm also somewhere there, but it's not so easy to see. The process has one advantage. It can take plastic and biomass together, which means the plastic that we take from the AD doesn't need to be very clean. We just have to press out the water. We can deal in the same process with the attached biomass and make both into oil. Plastic has somewhere about 60 to 90% conversion rate, and biomass is about 30 to 50, depending on how much is the lignin content. So with these two processes, we have the raw material that can then be converted to energy. Now, the question is, how shall we convert this raw material into energy? Yes, sure. It can be done in a pyrolysis. It can be done in a fired reactor. But the most mobile application for this is actually an internal combustion engine. And well, the only reason we are talking right now about electric engine is because these combustion engines, they have a typical efficiency of 25 to 30% if they run on gasoline. And if you run with a higher compression as diesel, you get about 35%. Now, I have been studying engines, well, I'm a German. I've been studying engines for many years, and I love engines. But I was always quite disappointed that nobody was able to create higher efficiencies. And over the years, I have come to realize if you have such a big cooling system on your engine, that is all energy that is wasted. And number two, if your engine can make so much noise, that is all compression power that is lost and not harvested. So with these two factors in place, obviously, energy efficiency cannot be very high. And that has led me to create a new type of engine. We call it the Cropp Hyper X PDT engine. It has basically twice the power at the same speed and produces half the waste. But in order to keep up with the new technologies, whereby Mr. Judek already mentioned, there is not just petrol and diesel and gas, there is also ammonia and hydrogen and maybe acetic acid, as what we have learned from another presentation today. This engine can take all types of fuel, which means you don't have to change anything in the engine. You press a button and it changes what fuel it takes. Now, the question is, how does that work? Okay, first I may explain. Hyper-X PDT stands for hyper-expansion. When you have your normal engine, it compresses, let's say, 1 to 12. Then you explode your mixture and then it decompresses 1 to 12. Our engine compresses also 1 to 12 if we have, let's say, petrol. But we decompress at a rate of 1 to 40. Now, what that means is when your exhaust valve opens in this engine, there is no more pressure left to make noise because all the pressure has been harvested to create motion, which is used either for transporting or for creating electricity in a generator. Now, secondly, if you don't have exhaust pressure to make noise, then you don't need a silencer. So you are saving on parts, you are saving on spares, you are saving on weight. Also, this engine is it is not a 4-stroke, neither is it a 2-stroke. It is a single stroke. That means for every single turn, we have one full cycle of propulsion. Because of that, at the same speed, we can create twice the power of a conventional engine. Now, when you create so much power, you obviously also need to cool the engine. However, we don't want to waste the heat that is captured in the engine. So what we do is we send water to specific places in this engine to create steam. What does the steam do? It pushes the piston in order to create torque and motion, meaning the heat that normally is cooled away from the engine and basically heats up the environment. In this engine is used to perform work, and that creates an efficiency which is combined 30 to 50% higher than any conventional engine currently being considered to be built. Now, the last part is about friction. Sure, when you turn a motor by hand, it may not seem that much, but friction is still a source of losses, not just in efficiency, but also material. When you have friction, you wear off your frictional parts, meaning you have to refurbish the engine, and because of wear, and that is costly. Now, we call this engine a PDT, a positive displacement turbine, for a reason. A turbine has blades. When the material goes through the turbine, it is converted into power by changing the direction or the impulse of the motion. However, when you stop a turbine shaft, the material can still go through, meaning you have a bypass loss. But on the other hand, you don't have any friction loss because the turbine blades don't touch the housing. In our engine, we have a turbine-like motion, but we have some contact with the housing in such a way that we don't have friction. And because we have that contact, we can hold the shaft and no material will go through, which means we have no bypass loss. That is called positive displacement, because the piston positively displaces the volume that is being pumped by the engine, and therefore, when you stop the shaft, no more material is moving. So the bypass loss is eliminated. Now, because we have one explosion for every single turn of the shaft, we have double the power at the same speed. And together with the savings in heat wastage as well as combustion pressure wastage, we have a 30 to 50% more efficient overall engine. Because of that, the engine can be much smaller. And if it's not enough, these engines can be stacked in a modular configuration. That means you imagine similar like a pizza, which is a bit thick, and you put a few pizzas on top of each other, and you have a multi-cylinder engine. Now, if that is still not enough, this engine, because it is turbine-like, can run at speeds way higher than a conventional motor. Yes, I know, Formula One will run up to 17,000 RPM, but most car engines or generator engines, they run 3,000 to 7,000 RPM only. This engine can run up to 40,000. And obviously, if you have 100 horsepower at 5,000 RPM, you will have about 200 horsepower if you run 10,000 RPM. So without actually changing the engine size, simply by running it faster, you can create more power. In this engine, we are able to run at 10,000 RPM, but to control the fuel and the explosion rate to such a degree that we only combust as if we are running at 5,000 RPM. Because of this, we don't need a gearbox. And because we don't need a gearbox, we are fully compatible with electric motors, which can be changed in speed much more than a conventional engine. And because of that, we can directly couple our engine with an electric motor and have a hybrid straight away. Now, Elon Musk may like this because in his Tesla, there is no space to put a combustion engine because all very tightly designed. But since this engine is so small, he could consider to couple it up with his electric motor and straight away have a hybrid, since no space for cooling system and for exhaust is required. So I want to conclude this presentation with this statement that in order for a better environment, we need to have first a better thinking within. And I sincerely believe that the age of the internal combustion engine is about to be restarted. Why? Because even if we want to run everything on electric engines, we cannot create all that energy simply from wind and solar and hydro alone. We have applications that require materials to be combusted so that that energy can be decentralized. And we have a lot of waste that we don't want to put in a landfill. So we better take that waste and convert it into a transportable form of energy, which then is converted to energy in an internal combustion engine that gives you 30 to 50% higher output for the same amount of fuel. I hope we will all have one very soon. Thank you very much.
Yeah, thank you very much, Dr. Richard Cropp. Is there any questions? Is there any questions to ask about his presentation? Then. So I hope we can close the session now, and we will meet together again soon. It's better if everyone involves. Otherwise, we can close with the session. Yeah, okay. Thank you very much. Have a nice day.
Sama-sama, as we say in Malaysia.
Yeah, thank you very much. We'll meet again soon. Thank you very much. Bye. I will send you the presentations to your emails.